So a few notes. So del is the operator, and it can operate on a vector field. So if you do, now here comes the cool stuff. So this is a divergence operation. That's called divergence. And the output of this operation is a scalar. It's no longer a vector. Okay? And when you're doing a curl operation, the output of that is another vector. And when you're doing the gradient of a function, so that's called a gradient, that output is also a vector. Okay? So if I look at it, a gradient of a function, the dot product of a gradient of a function with the gradient of another function, this is like okay. That's a legitimate operation because we got dot product between two vectors. Okay? But saying I'm going to do the dot product, the divergence of a divergence is not allowed. Because the output of a divergence operation is a scalar. So this will be a scalar. So you can't do the divergence of a scalar. Okay, so be really, this is the reason I'm warning you guys, because it's like really easy to do this kind of stuff on a test or problem or whatever. So, and then also sort of a gradient of recurl is also not allowed. So just be careful about what's allowed. I mean, just like make sure you're doing the operations on the right thing. Sure. Okay. All right, guys. So now the fun part of anything I do is like historical background of how we get to. So that was all. So again, we went through coordinate space as a reminder, cylindrical, Cartesian, blah, blah, blah. We looked at a few operators, and now we're going to talk about how Maxwell's equations were created historically. The reason is that it does make it, I think, a little bit more understandable. So these Maxwell's equations are like the most important equations we have as electrical engineers, or most important connection with physics, I believe. I mean, there's quantum stuff that we do for semiconductors, which is what I work on, but the biggest thing that all electrical engineers, so from resistors, capacitors, we looked at transmission lines, lighting, everything, is coming out of these Maxwell's equations. So these four equations define everything we do at the core, from like DC values up to, and they're like valid up to like 10 to the 15, 10 to the 16 hertz operation. So really anything you run into is these four Maxwell's equations. So historically, what had happened was stuff for electricity and magnetism got developed, like our ideas of how these two forces function developed independently in our history, and then Maxwell's equations link these two things together, and then we have electromagnetism. Okay, so first, think about in terms of, and so basically, it's a way of linking. One way to think about it is that linking electricity with magnetism. Another way is looking at electromagnetic fields. A lot of physicists think they're really the same core fundamental thing, and they show themselves in different ways. But they're both really old. So like when we really had no science or hokey science, they were still seeing these. So for example, going back to like ancient Greeks or whatever, they noticed that if you had some kind of a rod that wasn't like non-metallic rod, and you rubbed it with some silk or something, you could like pick up small particles with it, like a piece of paper or something you can pick up with that. Okay, so they notice there's this thing that if you, again, like you're doing something to this rod, it's like grabbing something, and like it's doing something. So it's an indication that something's happening with this rod. That was like the first indications. And then the first guy that actually came up with a model of charges, basically a description of what was going on here, which is that you are either removing the silk, or whatever you're doing is either removing this thing called a charge from this rod, or adding something called a charge to this rod. Believe it or not, was our own Ben Franklin, yay. So he's the guy who came up with the concept of charge, which is pretty freaking amazing. Have you guys read about Benjamin Franklin? So this dude, okay, I love this guy. So this is back in the day, right? Back in the day, they didn't have like university. Sorry, I'm going to go off on a tangent for a minute here on Ben Franklin, because it's so amazing. So they didn't have universities and schools, blah, 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 especially in the U.S., which at that point was not the U.S. It was like, he's originally from Boston. He was born in Boston. And so I think his brother was in the printing business. So you'd get to a certain age, you would get a sort of indentured essentially to somebody who had, if you wanted to make something out of yourself, you would get indentured to somebody who had a skill. In this case, his brother was a printer, printed newspapers or whatever, did print jobs for people, and in Boston. And Ben Franklin, being who Ben Franklin was, I guess his brother was an asshole, or he didn't like to be told what to do. He ran away. So when you do that, you're agreeing to bond yourself to this person essentially, and so you're giving him free labor. In exchange is teaching you something. So it's kind of like getting a student loan, I guess, right? So, and so he got out of there, had enough of it. He went to Philadelphia, which is mostly well known for, and sort of gradually did a bunch of crazy things, but mostly around the printing business. Eventually built his own printing business, blah, blah, blah. And he's always like this curious guy doing all sorts of stuff, and a funny guy. I don't know if I'd suggest you guys read about his biography and all this amazing guy. So eventually he got wealthy enough as a business person, I think by about his early 40s, that he just retired. And that's when he became a scientist. That's when he made a scientific name, which was legit. He was like internationally known in his time as like a major scientist internationally, all from stuff that he did after he became retired. Let's just say my retirement has not been as fruitful. But and then this is, the coming up with the concept of charge is pretty amazing. So anyway, he's the guy who came up with that. The only bad thing he did is he made the charge of an electron negative. Could have gone either way. So we wouldn't have to be dealing with with currents. You guys know if the currents, like the electrons are going this way, the current's going that way because the charge, anyway, that's not a minor thing. So anyway, he also came up with that negative thing, okay? So he just came up with that concept. He didn't have a measurement of a charge. He just described that phenomenon as I'm removing this thing called a charge from one thing to another. So magnetism, so this is like sort of the electric field charge concepts coming up. There's no indication that this is related at all to another thing that was magnetism. So again, people had this thing called a lodestone that, would kind of rub it against a piece of metal, and it would make that piece. Then if you, took that piece of metal, you put it on something that was bobbing on, in water or something, it would point in a certain direction. So you would be magnifying a piece of metal, and you can use it for a compass. Again, this is like really old from the old Greeks. So these is like before there's like legit science. So you can imagine, Ben Franklin didn't know what derivatives were. I'm sure maybe he knew. I don't know. It was after Newton and Leibniz. So there was the concept existed, but I just don't know if he knew. This is like at the level of they started looking at electricity and magnetism. Then I don't know when this happened. I'm going to guess it was the 1700s or early 1800s. There was this guy called Charles Coulomb. I think it was a French guy. And he came up with a really intricate experiments to isolate electric charge and try to measure, and not try, but he measured the force caused by these charges, okay? So he discovered that these electric charges that were causing this force, this electric force, the force from them would decay by 1 over r squared type of function. That's what Coulomb discovered with his experiment. So he was just, again, we've got electricity and magnetism. There's no indication that they're related. They're just two forces, like gravity is a force, right? So this is what people are thinking at that point. And so this concept of 1 over r squared was already, like Newton had already come up with that. And so it makes me think that Coulomb, again, I don't remember exactly when he came up with this, but it was probably in the 1800s, so this idea of 1 over r squared type of function was good. So Coulomb's law is, I write you guys Coulomb's law here, is, so this is something that hopefully you guys saw in, lower division physics, electromagnetics, that if you have two charges at R, let's call R1. So remember, R1 is a position vector. It defines the location of that point with respect to the origin. So if you had a charge Q at R1, and then you had another charge Q2, so you call this Q1, you had to call Q2 at R2. So those two would give you, if you subtracted those two, you'd get a vector R. It's pointing from one to the other. So basically Coulomb's law was, he'd figured out that the force, you always have to, when you have Coulomb's law, you always have two charges, and you always have to define the force on which given which. So you always say the force, for example, in this case I'm writing F2, means the force on charge 2 caused by all the other charges, or in this case just charge 1. That is equal to some factor k, the value of the two charges multiplied by each other over the distance between the two squared. And that force has a vector direction r hat. Okay, So it's basically pointing, in this case it'd be like sort of r hat would be pointing in that direction. So everything we know about two charges acting on each other is in this equation. Okay, the direction, the fact that you multiply the value, the two charges together to get, that's related to the force, and the force is related as 1 over the distance squared. Okay. And again, r hat is, or sorry, not r hat, vector r is position vector r2 minus position vector r1. And I don't know, I guess he's the guy who came up with this. I don't know if he did or not, but that this factor k is 1 over 4 pi epsilon naught. And epsilon naught is defined as the permittivity of free space. By the way, sorry, this is the force, the way it's written here is the force as if these charges were in a vacuum or so-called free space. Okay, so that's why you have the permittivity of free space, and this epsilon naught in SI units is 8.85 times 10 to the minus 12, whoops. Farads per meter. If these two charges were in, say, something else other than free space, let's say these two charges were in water or something like that, or someplace else, then the force would get more, basically would get less, sorry. The force would get less than in vacuum. So the force on stuff in a vacuum is the maximum, and in other things it's less. Okay? What's that?
Medium.
What's that?
Sorry, other mediums.
Other mediums, thank you, mediums, yes. And so that stuff ends up being the dielectric constant of those mediums. So if you were going to do the same equation in another medium, you would have, say, you have the dielectric constant of air, which is close to 1. And then you'd have water and other things, right? Dielectric constant of your printed circuit board material and all those kind of things. And because that would get multiplied by, so a general thing would be the epsilon naught would get multiplied by that dielectric constant, and you can see because that's in the denominator, that would make that force less. So I have the maximum force between these two charges would be in a vacuum. Any other medium, it would be less. And what the sort of the parameter that tells you how much less is the dielectric constant of that medium. Okay, so this is Coulomb's law. Okay, you guys remember Coulomb's law? Good old Coulomb's law. Okay, so that's Coulomb's law. So then now let's just jump back to magnetism for a second. So it's just sort of showing like these are kind of like developments as things are developing. Then there's this guy on the magnetism front, the guy named Ørsted. I'm not going to write these guys for amusement. That noticed that it's not just this lodestone stuff that you rub against a piece of metal that makes it magnetic, but that a current can have these magnetic functions. So Ørsted noticed that a current basically can deflect a magnet. So again, if you had your compass, if you're running a current close to your compass, it would kind of screw up the compass. This is what this guy came up with. So, and from there's a guy named Ampere who gave this thing basically came up with Ampere's law, which sort of defines how a current creates a magnetic field. So that's a complicated expression. I'm going to leave that for the second until we get in a few more minutes. I'll write it down. But that was Ampere that came up with the idea that or came up with an expression for the fact that a current basically creates a magnetic field. Okay, so again, Coulomb, Ampere, this kind of thing. So simultaneously, okay, maybe from the get-go, from the time Coulomb came up with this idea, and Ampere came up with this idea, people were really uncomfortable with this idea of action at a distance. What do I mean by that? Like if I'm pushing this piece of paper, okay, you guys we all agree it's pretty easy to see. I'm pushing on this thing, pulling on it, whatever. So that's a force. It's kind of hard to get your head around this force that's making something move that's not connected to what you believe is moving it. Okay, so if you guys, again, mechanically, Newton's talking about gravity being this action at a distance. The Earth is not connected physically to the moon, but it's having a force on it, etc. People were very uncomfortable with this. Okay, we're still uncomfortable with this, as a matter of fact. Okay, so people came up with the idea of something called a field. Okay, a field is completely a made-up concept. Okay, I think I've said this a bunch of other times. It's very hard, it makes your head hurt, because you feel betrayed after all these years of people being told about electric fields and magnetic fields and all that stuff. The only thing we can measure is force. We can't even measure force. What we can measure is a change in direction of velocity and a change in position. That's all we can measure, which those two things give us acceleration, that with the mass gives us a force, so that's the only thing we can actually say we measure. Field is something people have completely come up with to make themselves more comfortable with this concept of action at a distance, okay? And this is the idea, is you say, so Coulomb's law really exists if you have two charges. One of them is creating force, either they're attracting each other or repelling each other. That you can actually create that situation, okay? An electric field is a concept that if I had a charge, so forget about the second charge. If I had a charge, this thing would create this electric field all over the universe. This charge, the charge on this, the charge on this one electron is creating this electric field that I can define the moon, Alpha Centauri, wherever, right? It's very small. It's dropping off as 1 over r squared everywhere. But there would be this electric field everywhere. And if I brought a test charge and dropped it off any point in this field, it would have a force acting on it because of this guy. So it's purely a concept to help you try to understand this action at a distance, to help you do equations, sort of explain laws. So that's the concept of a force. Of an electric field, or any kind of field. So in the case of an electric field, what people did was they said, okay, I'm going to take this force and I'm going to define something called a field caused by, so that's the force from 2 to 1. So electric field created by Q1, is I'm going to take out Q2 out of this equation. So I'm just going to have KQ1 over R, whoops, over the vector R squared times R hat. And I'm going to define that for everywhere in space. So notice I took Q2 out of this equation, so I could bring in Q3, Q4, anything into this field, and like I can just assume that that field is existing even before I bring in a Q2. I don't know if that helps you guys or hurts you guys or whatever, but so like actually there is no electric field because until I bring a Q2 into this picture, there's no force on anything. But, okay. You guys with me, against me? So okay, so that's the definition of a field. Okay, so that's, people start coming up, so now Coulomb's law, Ampere's law, concept of an electric field got created. So that's where we're at. Then the next thing is people discovered that, I don't know who discovered it, but it's called the Biot, and I'm probably mispronouncing that, Savart law. So back to magnetism. People discovered that if you had two current loops, so there's a current running through here, let's say, and a current running here, and if you just looked at any particular segment here, so you took this segment and looked at those two segments, that these two actual loops, like actual wires, would either be attracting each other or repelling each other, depending on the relative direction of the currents. Okay, and that's called and this guy Biot Savart, I guess, developed the concept of a magnetic field around this attraction. Again, the only thing we can measure is force. So if these things are attracting, these two wires are attracting or repelling each other, you can measure a force because they're actually changing their location. Okay, so you can measure force, so then you can define something called a field by, so this Biot Savart law came up with the concept of a magnetic field and sort of the incremental value of this magnetic field caused by an incremental length of wire here is 1/4 pi r squared, where r is the distance between these guys. I1 dl curl of r hat, where r is defined as perpendicular to this dl increment. So if I was here, my dl, in this segment, dl would be pointing in that direction, and r would be perpendicular to that. It's called the Biot Savart. Okay. Now, and this led to Ampere's law. which is describing a closed loop scenario. Okay, so the Biot-Savart law is kind of like fundamental, I guess, is how you look at it. Ampere's law is just taking the case of this in a closed loop. So it's doing a line integral of the magnetic flux on length. And it basically says if I do that, it's equal to all the currents that I enclose. Or if you're talking about, so H is the magnetic flux. So if I talk about the magnetic field, it would be B dot dl is mu naught I enclosed. And mu naught is this relationship between the magnetic field and magnetic flux called the permeability of free space. And this is equal to 4 pi times 10 to the minus 7 henries per meter. By the way, this is like also a hint about how these are related to like electric circuits, because notice the permeability, at least in SI units. There's a bunch of units for both permittivity and permeability. But here, notice how this is given in henries per meter. Henry is a unit of inductance. So sort of a hint that it's this magnetic field, magnetic flux that's leading to inductors or inductive phenomenon. And same thing with, notice at least in SI units, the permittivity is given in farads per meter. And again, a hint that, it's the units of capacitance. And so there's this relationship between electric field and capacitance, okay, in some way. So again, this, by the way, this integral is part of that lasso of the curl. Remember I was talking about the curl is this lasso, it's a line integral, and basically says that if I have this line integral, means that if I have currents, like a bunch of wires carrying currents, and I put a lasso around all of them, okay, this line. So if I have a bunch of lines carrying current, so I1, I2, there's another current, I3, and I put my lasso around all of these lines, okay, the magnetic field enclosing these lines, the integral of the magnetic field enclosing these lines, the line integral. So if I sum up all the components of the magnetic field along those things, it's equal to the sum of all the currents inside that. In a lasso kind of situation. Okay? And that only works in magnetism, again, going back to my example that maybe didn't make a lot of sense, is you can only think of that in terms of something that's grabbing, like going around a line. You can't kind of put a lasso around the point charge. Okay? So this function of this, if you did this for electric field, you would get just 0. If I, instead of H, I had E here and I integrated E around some charge, but a line, I would get 0. So this is Ampere's law. By the way, the relationship, of course, the relationship obviously between B and H is given by this mu. And B is called the magnetic field or magnetic field or magnetic induction. And H is called the magnetic flux. Okay, so again, electric, this is where things were at that time of the Ampere's law. So now you have an electric field and a magnetic field, okay? Electric field is defined as the electric force divided by a test charge. And, oh no. And the electric field is generally a function of both position and time, and it's given in volts per meter. And the source of this thing is a charge. So source is charge. For some reason I can't charge this thing and just give me 1 second, guys. See if I can charge and display. Oh, okay, good. I think it's my cable. All right. All right, so that's the electric field. So its electric field is caused by charge. Magnetic field is B, and it's also a function of position and time. It's actually, this one, B, is usually actually flux density. And this is given in Teslas. And H is also, again, function of position and time, and this is called the H field. This is in amps per meter. And the source, so the source of this guy is charge. The source of these guys is current. So if strictly speaking, if this was a material science class, you can also obviously get magnetic field because of polarization and material, like that lodestone I was telling you guys. You don't only need a current, but because we're electrical engineers, in our world, a charge sitting in a non-moving only creates electric fields, okay? And a current, which is a charge moving charge, only creates magnetic fields, okay? All right. Yeah, sure.
What does that say? Vector E equals vector F over current.
Oh, it's over a test charge. Because the force is between two charges. If I want to introduce this concept of electric field, I have to sort of remove that second charge, theoretically, and put in a test charge there. Okay. All right. So again, sort of saying the same thing here in a different way is basically you end up with a charge at the beginning point that gives you this electric flux density, which is a vector. And by using the permittivity relationship, that gives me the electric field, and the electric field gives me the force. Okay, so this is what I can actually measure and see. And D is again epsilon naught E in free space, or anywhere else is epsilon naught whatever the relative relative permittivity is in anywhere else. Okay. And then I think of B as being mu naught mu R times H. So similar to this, basically a current gives rise to this H field, which so these are like sort of the correspondences between flux densities and fields for electricism and magnetism. So you have charge leading to flux density, leading to electric field, leading to force, and in magnetism you have current leading to magnetic flux density, leading to magnetic field, leading to a force. And again, that's the only thing you can actually measure. Okay, so now, so this is where things were at, and so, I'm saying like you get an isolated charge, you have a current, but of course current is a moving charge, right? So that's all it is current is charge moving around. So people ended up with something called this next level thing, which starts hinting at the relationship between electric field and magnetic field. They came up with something called a Lorentz force. So not a magnetic field, not an electric field, but the union of both. So that is equal to Q test charge times the electric field. So that's the electric force, plus the velocity of that test charge cross B, the magnetic field. It's the Lorentz force. So, what do I want to say about this? Okay. Trying to think of what bogus example I can give you guys. The only thing I can come up with is like these like cyclotrons, or I'm sure everybody's like seen these, they launch these like charged particles into like magnetic fields, or it could be a combination of electric and magnetic fields. So let's say you did that, right? So you have this sort of this charge, this test charge, shooting through your whatever charge accelerator or whatever it is. If you have the magnetic field pointed in this direction with respect to the charge, so you actually create a velocity for that charge, and you're physically making that guy shoot into this experimental piece of equipment, and you have strong magnets running perpendicular to this direction, so you end up with the curl, so sorry, not the curl, the cross of the magnetic field with the velocity of this thing will give you the direction of travel, of the direction of change of the electron. So it's putting, so if my magnetic field is running like this, remember we got this curl operation, I got V cross B. Okay, so B has to be this way, B is that way. So the force on this charge will push it up, and you start seeing those, and we've all seen tracks, right? You guys seen these like particle tracks at particle accelerators where, you guys seen this? No? Where these things get deflected, and through that they can tell the mass of a particle. You guys seen this stuff? No? Yeah, okay. So that's why it has that trajectory, because you got this sort of V cross B. And then if the electric field doesn't really help you in that direction, because it's just pushing you in, maybe it does, but it's gonna, like, if it's the electric field is pointing vertically, it's just gonna push you out that way. So depending on which you would put it, but that's the electric field is pushing things. First of all, the charge doesn't have to be moving for the electric field to affect it, okay? So notice the Lorentz force says that the electric field, there's a force on this sort of charge, whether it's moving or not. The electric field times this charge, that's the same as electric force, right? Coulomb's law kind of thing. But if the velocity of that test charge is 0, so it's not moving, okay, then there's no force on it. There's no magnetic force on it. It's only when it's moving, and when it's moving in this sort of this cross product with respect to the magnetic field that you'll get a force on it. All right, I always hate magnetic fields. I don't know why, because of this cross thing. I always have to keep track of this crap. Okay, so let's go back to some of the examples I was telling Daniel about sort of rewriting some of these functions. So if I do this operation of D dot S, remember this was this operation where basically shrinking this volume around the charge. So this says if I have a volume and I'm shrinking it around this charge, I'm going to get, this is going to give me the enclosed charge. And also earlier I was saying that integral of H dot dl gives me the enclosed current. So this is a line integral, this is a surface integral. So the source, this also tells you that the source of this D, which is this electric flux density, which means the source of electric field, is charge or charge density. And the source of, remember this was also the curl equation, so this is the same as, so this curl, this is the current density. So this is all the enclosed current. So this J is the current density. So J is just equal to current divided by area. Bless you. So by the way, this is, I don't know if you guys remember this stuff, but this is called Gauss's law. I guess this is called the Ampere's law. Bless you. So this is the same as another way to look at it is sometimes they talk about rho, which is the charge density. And del dot B is always equal to 0 because magnetic fields don't have a source. So this is going back to our earlier discussion that basically this del dot D, or this divergence of like electric flux or electric field, can give you a non-zero value because D or E are being created by isolated charges. Okay, but del dot B, the divergence of the electric field, always gives you 0 because there's no such thing as an isolated charge. You're never going to find that anywhere. Do you guys kind of see that? Does that make sense? So if, like, imagine if I had, well, anyway, let's just be okay. So the next thing is Faraday's law. By the way, none of these guys named these laws after themselves because that would be bad behavior. Other people named it after them. So they're humble people. Faraday's law. Well, they came up with it. So, okay. So Faraday's law, what they noticed that if you had a open wire, okay, and then you had a magnet. So you had an open loop wire, no current going through it, and you move this sort of magnet around this wire, okay, that it would lead to this potential, this EMF around the open parts of this wire. Okay, we don't have time. Close. Okay. And so EMF, you guys are gonna have to look it up. It's called, have you guys seen, I don't know if you've seen it, but I'd like not seen this definition. It's called the electromotive force. So electromotive force basically is something that gets created when you have a mechanical or a battery or something like that giving rise to an electric field. So it's called EMF. So it gives you an electric potential difference. So you notice basically that if you move a magnet around this wire, it actually creates this potential which is related to electric field. So you start seeing this link between these things. Okay, so if you just if there was no magnetic field and you took the integral of the electric field around the closed loop, you would always get a zero. Because you always, when you have an electric field, if you go along any direction and get back to it, you always have done zero work. Because part of the time the electric field is repelling you, part of the time the electric field is attracting you. You know, we could drive that, but we won't. So that's normally the case. So which means that, you know, if you had a enclosed, so okay, because of that, right? So let's leave it at that. What else do I want to say about that? So Faraday, so this is like if you just had an electric field. So what Faraday found out that since in this case, if you have this EMF, this integral of E dot dl is not equal to zero. So provided there's a magnetic field. And so he added this new thing, Faraday did, to this equation. And he basically said that E dot dl is equal to this new factor, which is sigma, he called it, this is psi, pronounced psi. And it's related to magnetic flux. Okay. Or another way to put this is E dot dl minus d psi dt is equal to zero. Or another way to write this is curl of E is minus d by dt B. So this is two ways to write Faraday's law. So, but what that's saying is, he noticed that basically this is a definition that if you have a changing magnetic field that's changing with time, it's giving rise to a potential. Okay, that's Faraday's law. So all the motors and electric motors and stuff run like this, right? You have either you have like an engine that's rotating a magnetic field or something like that, creating a voltage, so that's your generator. Or like, let's say if you have an electric car, you're going the other way. You're generating a moving thing based on this voltage. Okay, so that's Faraday's law. Okay, so I'm just gonna stop, just write one last thing here. Four last things, which is getting us to Maxwell's equations. Okay, so these things we're summing up all the stuff that we talked about so far. Minus dB dt del cross H is equal to the current density del dot D. So this is Faraday's law. This is Ampere's law. This is charge density. This is Gauss's law. And del dot B, I forgot that. I guess this didn't have really a law, but it was just this function. So this is where things stood when Maxwell came there. So he didn't create, these are close to being the Maxwell's equations, but not complete, okay? but this is where didn't create all of these things. There was all this whole batch of characters that were building on each other work, and this is the situation where the situation was when Maxwell started looking at this stuff. And sort of Maxwell's contribution was that he realized this wasn't quite complete, that there is also a relationship between a changing electric field and the magnetic flux. So this was contribution. This is what I would love to do, to come in and put in the last thing and call it your law. He didn't call it his law. Some other people did. Okay? This was his addition. He noticed that if you had a changing electric field, that would also create a magnetic field. Okay? So this, with the addition of what I put in red there, this is known as Maxwell's equations. These 4 equations describe everything we know about electricity, magnetism, resistance, capacitance, inductance, everything you guys do besides quantum physics and electrical engineering is coming from these 4 equations that then get sort of evaluated, specialized, turn into rule of thumb, and turn into like R's and C's and things. Everything comes from this. And this gives me like freaking goosebumps every time I look at these things, believe it or not. It's kind of a weird kind of guy. But so notice one of the key things here. So you have a changing magnetic field is causing an electric field, and a changing electric field is causing a magnetic field. Okay? So this gives you electromagnetic waves. That's why we can have electromagnetic waves. Because you can basically launch something as the electric field is changing, it's changing the magnetic field, which then goes and changes an electric field, it changes the magnetic field. So that's like the basis of, we looked at the transmission lines as if they were just R's and C's and L's, but those were simplifications, just like I'm saying is, magnetic, these things are, the magnetic field is, we simplified it, is in inductance and circuit theory. We simplify electric field as capacitance in electric field theory, but in fact, what's going on is you're launching these changing electromagnetic fields into your transmission line wires, and those are what's traveling across. Because of this relationship is why you get a wave going through, if you look at it from an electromagnetic way, why you're getting this waves through transmission line. It's why you get light gets from here to there. Light is also an electromagnetic field, okay? So that's why you have fiber optic cable, that's why you get light to travel. So if this not hold, I guess we wouldn't have light. It's interesting, but so it is like very, 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 very fundamental equations here. That's why it's just amazing. It's very fundamental, but in some sense, like very simple. Like if you go into looking at quantum physics, like you never see this kind of math, these kind of definitions. Right? They just don't exist. Okay, thanks guys, thanks for your patience.